Further application of the solution of partial differential equation, we shall study the solution of wave equation. A wave is a physical entity which is periodic in space and time and carries energy with it. If we want to describe a wave by means of a differential equation, then it is the equation where u or t is the wave amplitude. U or t is wave amplitude. If we want to solve this by method of separation of variable, we must keep in mind that the solution u must be periodic in space as well as in time. V is the velocity of propagation of the monochromatic wave, and V for elastic wave, it is related to the elastic moduli or respective elastic moduli, and for electromagnetic wave it is related to permittivity and permeability of the space through which the medium propagates. So using separation of variable technique, we write it as phi of r and t of t, and if we substitute this equation there for non-trivial solution, we get this is 1 by phi of r, nabla operating on phi of r on left hand side, and on right hand side we have 1 by v square t of t d2 t dt2. The left hand side is a function of r only space variable, and right hand side is a function of time. So we call this as minus alpha square, where alpha is real. We choose the separation variable in such a way that the periodicity with respect to time is ensured. So we get the solution is d2t dt2 plus alpha v whole square t is equal to 0, or we write it d2t dt2 plus omega square t is equal to 0, where omega square is equal to alpha times v, but we know that it is k times v, so where k is the propagation constant, so this separation constant is actually propagation constant k. So the t solution is of the form e to the power plus minus I omega t, or we may choose it as a sin omega t plus b cos omega t. However, this part becomes nabla square phi of r plus this is k square phi of r is equal to 0. This is a very important relation of mathematical physics, and it is known as Helmholtz equation. This is also a partial differential equation in space variable. So we see that if we want to solve the partial wave equation, then if we demand that the wave amplitude must be periodic in time, then the time part has the same behavior for all the waves, while the space part reduces to the solution of Helmholtz equation. The solution of Helmholtz equation depends on the geometry under consideration. So although the time part has same behavior for all the waves, the space part differs from one wave to another. So the solution of wave equation now reduces to the solution of Helmholtz equation. Before going to discuss the vibration, the transverse wave, in strings and membranes, we shall first make a general discussion on the different wavefronts that we generally use. That is the plane wave, spherical wave, cylindrical wave. So our aim is to solve Helmholtz equation for different cases where k is a real quantity. First we call plane wave. We come to the case of plane wave. A plane wave is one for which the wavefront is a plane. That is, all the points lying in a plane has the same phase factor, and the wave propagates in a direction perpendicular to this constant equiphase surface. This is known as plane wave. A plane wave can be realized from a point source when we observe it at a very large distance. So the waves that is originated from a point source, and if it propagates in an isotropic and homogeneous medium, isotropic medium, then on the surface of a sphere centered at the point source, all the points will have same phase, so the wavefront is spherical. If we observe this wave, spherical wave, in asymptotic region, then a portion of the spherical surface will appear to be a plane, and we call it a plane wave. Another way of realizing plane wave is this. Consider an xy plane. Consider an xy plane, and we arrange identical coherent point sources symmetrically on xy plane, and we assume the wave propagation in z direction. Then each point on this surface, if we call it as the z is equal to 0 surface, from each point the spherical wave will be generated from each point, and this wave propagates in all the possible direction isotropically. We will have propagation in all possible direction. If we consider the points not near the end or edges of the strip within, then the amount of energy that is flowing in the lateral direction to the right is exactly equal to the amount of energy flowing laterally to the left, and this is same for the upward, the x direction, positive x direction and negative x direction. So overall, except near the edges of the plate, there is no lateral flow of energy, and all the energy flows along the z direction. And if we consider z is equal to constant surface, then the same amount of energy, all the waves that are generated from there will cross this surface at the same time. So the wavefront will be a plane one, and furthermore, the same amount of energy crosses each of such plate during the same interval of time, so that the wave amplitude does not die out with distance. That is, a plane wave is one for which the wave amplitude is independent of the space variable. Another way, if we consider this is the direction normal to the wave propagation n cap, then any point, if we consider any point on this plane, have the property that n cap dot r is equal to constant. So the total phase, if we consider, that should be of the form k dot r minus omega t times I. This should be the phase for a plane wave. Let us see what we get from the solution of wave equation. If we solve Helmholtz equation, in 3D Cartesian system, Cartesian coordinates, looks like del 2 del x2 del del 2 del y2 del 2 del z2 times phi of x y z plus k square of phi of x y z is equal to 0. This is the Helmholtz equation when we apply it to 3D Cartesian system. As per separation of variable technique, we use phi of x y z as capital X of x, capital Y of y, and capital Z of z. As for convention, capital X depends on x only, capital Y on y only, and capital Z on z only. We plug this into this, and for non-trivial solution we divide all alone by x y z. So the result is 1 by x d2x dx2. Note that if one use this notation in this place, it is totally wrong because capital X is a function of small x only. So use of the notation partial derivative is erroneous, and a serious penalty may be faced in examination. For non-trivial solution, we keep this x part on one side and take all them on the another side, so that this is the left hand side is a function of x only and right hand side is a function of x and y, and we know that solution will have periodicity with respect to x. Keeping this in mind, we take separation constant as this, where kx is real, so that x equation becomes d2x dx2 plus kx square x is equal to 0, whose solution is x is equal capital X of e to the power plus minus I kx x. We take the solution in the form of traveling wave. Then this part we take 1 by y d2y dy2 plus 1 by z d2z dz2 plus k square is equal to minus kx square. We take kx square on this side, so this is made positive and is equal to 0. If we take y part on the other side, then we say the left hand side is a function of y only, while right hand side is a function of z only. Keeping in mind, sorry, I have made a mistake. If this is minus, then this should be plus, and if this happens to be plus, then this kx square must be minus, and this should be ky square when ky is again real. So that y equation becomes d2y dy2 plus ky square y is equal to 0, which gives you the solution y of ky y is of the form of e to the power plus minus I ky y. Now we come to the z equation. We see that z equation becomes d2z dz2 plus k square minus kx square minus ky square z is equal to 0. We call it kz square, so that k square is equal to kx square plus ky square plus kz square, and the z equation has the solution So the total solution is, so the special part of the solution is kx x plus ky y plus kz z, which is of the form plus minus e to the power k dot r, where we call the wave vector k, we define the wave vector k is n cap k, where n cap is the direction of propagation. So we see that the space part has this form. So if we consider plane wave u of rt, it has the variation a e to the power plus minus I k dot r minus omega t. If we take e to the power plus I k r as a wave, it is wave traveling along positive k direction. It is traveling along positive k direction, while e to the power minus I k dot r, it represents a wave which is traveling along negative k direction. So we see that what we argued as the form of the plane wave from physical justification corroborates with the mathematical finding. Now we come to spherical wave. A spherical wave, if we want to study the situation from physical consideration, a spherical wave is obtained when a point source is placed in a isotropic medium. Then the wave propagates in all directions identically. So to say, the wave amplitude is independent of the polar angles of the angles theta phi of spherical polar coordinate, and it has only r dependence. And the wave front is obviously a sphere which is centered at the point source. And at the same time, if we consider the amount of energy crossing the surface of a sphere must be same. So on the surface, if we consider intensity at a point r be this is intensity. This is the amount of energy crossing per unit area per unit time. And if we consider a surface, the surface of a sphere of radius r, then the total energy is energy per time, is the amount of energy crossing per unit time is equal to 4 pi r square times intensity, and this is independent of r. This should be independent of r. That means intensity must have 1 by r square dependence, that is amplitude u must have 1 by r dependence. So amplitude of a spherical wave must die down as 1 by r so that the total energy crossing the surface of a sphere remains the same. Now let us see what we get. And another thing, the phase part, in the case of plane wave, we get the phase part as e to the power I k r minus omega t. There is plus minus sign obviously, but this carries a vector character of r. But in the case of spherical wave, there is no theta phi dependence, so this part should be e to the power I k r minus omega t. Plus sign indicates a wave moving away from the source, and minus sign is that the wave traveling towards the sink. Now let us see what we get from the solution of wave equation. We are solving the Helmholtz equation. So for spherical wave, the Helmholtz equation is this part 1 by r square sine theta, then del r of r square sine theta del theta, del phi 2 plus k square. This may create a confusion, so I use psi, and this operates on psi. Psi of r theta phi plus k square psi of r theta phi is equal to 0. This is the Helmholtz equation. For spherical wave, psi of r theta phi is a function of r only, and there is no theta phi dependence, that is theta phi parts are constant, in which case this equation together with this becomes, this part you see that sine theta goes, so 1 by r square, this is per total derivative r square dr, and then coming to plus k square r is equal to 0 or d2r dr2 plus we first multiply this by, so do we get r square d2r dr2 plus twice r dr d small r plus k square r square r is equal to 0. This is the differential equation. We make a substitution like this: r of r is equal to r to the power n and w of r. We make a substitution so that dr becomes r to the power n w prime of r plus n r to the power n minus 1 w of r, and the second derivative part d2r dr2 we use Leibniz. If we substitute all these things in this equation, then we get this part, r to the power n plus 2 w double derivative of w plus twice n r to the power n plus 1, there is n minus 2 and this plus n into n minus 1 r to the power n times w. This is for the this term, and for this term we have 2n and this, sorry, simply 2 r to the plus 2n r to the power n w plus k square r to the power n plus 2 w is equal to 0. Because it is for r we will write r to the power n plus 2 r to the power n plus 2, or we have r to the power n plus 2 double derivative of w, first derivative term. If we collect this is 2 times n plus 1 r to the power n plus 1 w prime, and then these two terms when coupled together it is n into n plus 1, n into n plus 1 r to the power n plus k square r to the power n plus 2, entire thing is multiplied by w. So this is the resulting equation in terms of w. We set n, in this case n could be any finite quantity other than 0. So if we set n in such a way that the first derivative, there should be no first derivative term, in that case we set n is equal to minus 1, in which case this is not there and this term also disappears because n plus 1 is 0. So we are left with this differential equation w double prime, this is r to the power n plus 2, this is also r to the power n plus 2, k square w is equal to 0, which gives w as a function of r is e to the power plus minus kr, so that r part, r of r is equal to r to the power minus 1 w, this is e to the power plus minus ikr by r. This is the spherical wave. Wave amplitude falls as 1 by r. Now coming to cylindrical wave. A cylindrical wave is realized when identical points, coherent point sources are aligned symmetrically about a straight line, and which serves as the axis of the cylindrical waves. So if we consider this is the axis, and on this axis we place identical point sources, so these are the wavefronts that are being generated. And obviously if we consider a sphere whose axis lies with the axis is the line, source line, then we will have same phase at every point on this cylinder, curved surface of the cylinder, and one has to assume that this length is very high, so there is no end effect. That is, the length of this axis must be much greater than this fact. Now if we consider area intensity over there, the intensity over there must be rho dependent, must have rho dependence, and the surface area, if we calculate, this is if we consider a cylinder of unit length, then it is 2 pi rho into 1. This is this area, and this is independent of rho. That means I of rho must vary as 1 by rho, that is in amplitude rho must vary as 1 by root rho. This is the form of the amplitude as we assume from the physical consideration, and furthermore if we consider rho of t, then it should be 1 upon root rho e to the power I k rho minus omega t. This is this should be the form of the cylindrical wave. Now let's see what we get from the solution of this equation. In cylindrical coordinate system, nabla is equal to 1 by rho del del rho of rho del del rho plus 1 by rho del del 2 del phi 2 plus rho del 2 del z2. This is the nabla. But for cylindrical wave, it doesn't have phi and z dependence, so only this part is there, and this becomes 1 by rho dd rho of rho dd rho. So the Helmholtz equation is becomes, now Helmholtz equation becomes 1 by rho dd rho of rho d rho plus k square rho h is equal to 0. Here we have assumed that h of rho phi z is actually h of rho big phi of phi and big Z of Z, but for cylindrical wave this part is constant, so it is H only. So this is d2H d rho 2 This is the differential equation to be solved. As in the case of spherical wave, we assume let h of rho is equal to rho to the power n w of rho, and if we substitute this is rho to the power n plus 1 w double prime plus twice n rho to the power n w prime plus n into n minus 1 rho to the power n minus 1 w. This is from the first term. This is the first term. Then from this term we have rho to the power n w prime plus n rho to the power n minus 1 w. And finally the last term is k square rho to the power n plus 1 w is equal to 0, or rho to the power n plus 1 w double derivative, then we pick up these two terms. This is 2n plus 1 rho to the power n w prime. And if we collect these two terms, this is n square rho to the power n minus 1 plus k square rho to the power n, sorry, this is minus 1, this is plus 1, w is equal to 0. we set n such a way that this is 0, that is n is equal to minus half. So if we put n is equal to minus half, this equation becomes, with n is equal to half, sorry, n is equal to minus half, n is equal to minus half, this equation becomes w double prime, this is plus k square plus, you see this is 1 by 4 rho square w is equal to 0, which we approximate as w double prime plus k square w is equal to 0. We assume that rho is very high, and in which case we have w is equal, w of rho is of the form e to the power I k rho, so that this part gives you e to the power I k rho by root rho, as n is half minus half. So this is the form of the cylindrical wave. With this introduction to wave equation, in the next class we shall take up the case where the transverse vibration is set in a straight string.